Okay, so we have already discussed about core collapse supernova, right? We have discussed about the death of prompt shock, neutrino reheating, right? The modern theory of supernova, the two-stage process, core collapse supernova. Then we have talked about a binary system where one can be a red giant, another can be a white dwarf, and the white dwarf slowly accretes matter from the red giant star, and when it eats away, energy, explosive nuclear burning starts when the material hits the surface of the white dwarf, and as a result, a flash of energy is released. That is nova. Now, what if instead of white dwarf we have a neutron star? Then the same thing it happens. If happens, then the energy released will be much more. Okay, and it will be the X-rays will be emitted. So it will be X-ray burst. Previously, in the case of white dwarf nova, the frequency is much lower. But in the case of neutron star, the energy release will be much more. It will be X-ray burst. Same old concept. Now today I am talking about something different. We have talked about core collapse. We have talked about thermonuclear supernova. Now see, if we have a very massive star. Now when I am saying massive star, I am talking about this range 130 to 250 solar masses. Okay. Now, what happens? Not only that, I am also talking about low metallicity stars. Low metallicity stars I am talking about. Let's see what happens in these stars. Now, as you can understand, this is a very massive star. Okay. Now we have talked about big stars. What happens in very big stars? The photon, the energy density due to photons, this also becomes very important, because the pressure due to the energy density of the photons, actually it becomes more dominant than the gas pressure itself. And there, in very massive stars, it is basically the energy density of the photons which is resisting the gravitation. Okay, the inward pull of gravity. So here it is basically the radiation pressure which is the dominant enemy of gravity in resisting the contraction. Good, so far so good. Now you see, in such scenarios when the mass is very large, right, the temperature near the outer surfaces is also quite high. And right now I am talking about the outer layers. Here, the outer layers. The temperature is also quite large, and in fact the density is also very high. Now when I am talking about temperature, overall temperature, the outer layers is very large, and the density I am talking mostly about atoms, nuclei, and all that, everything, whatever is there. Now, in such scenarios, you see, here mainly it is the photons are present, because energy density of the photon is the one responsible for resisting the gravity. Okay. Now, in such scenarios, when the temperature and density are very high, then what happens is that, what happens? Pair production automatically starts happening. So, photons, they create electron-positron pair. Now, it's not a problem. It's a process we know. Now, it becomes a problem in the sense that this balance can be disrupted, because it was the photons, the radiation pressure of the photons, which was responsible to withstand the gravity. Now, if the photons, they keep on converting into electron-positron pair, what will happen is that all of a sudden the number of photons will start decreasing. So gravity, it remains the same, it will start become dominating. Now, another very interesting thing happens. In case of low metallicity, what happens is that the photon opacity is quite low. Okay, so this means that photons can easily pass on. They can travel and they can easily get converted to pairs, electron positron pairs. Now you might be considering, sir, we are talking about electron positron pairs. What about their pressure? It is not that much compared to the pressure, radiation pressure due to photons. So in a way, we are slightly losing the balance between gravity and radiation pressure. Now you see, if inside in this scenario, in these two important cases, that is mass in this range and low metallicity, what happens is that here the pair production rate, this particular mass range, is very high. And if the pair production rate is very high, and given the fact about the low photon opacity, that means they will not be absorbed, photons will not be absorbed, what happens is that more and more electron positron pairs will be created. Okay, so the problem is the high rate of production of the electron positron pairs. This is the main problem. And what happens as a result is that photons are removed at a very high rate. And so you can think of it like that. Initially they were equal in number. You can think of it. The gravity, this is photon. Now it is slowly decreasing, number of photons. So gravity will be the one to overcome. Very basic picture. Now, so as I was saying, the pressure support is slowly getting lost at a very high rate. Okay, now what happens? Gravity, when it dominates, it will start collapsing. Now when gravity starts collapsing, what will happen to the matter? What is inside? Is it vacuum? No, there is matter.
Yeah.
Now gravity will crush them more and more. Now when the gravity will start crushing them more and more, what will happen? The matter inside, what is the matter inside? Hydrogen, which is, I am talking about very massive stars, right? So maybe there is some sort of onion type structure inside, right? Oxygen burning, whatever structure is there. Now the very fact that the gravity is crushing them, what will happen? All the concentric shells, all the nuclei in the concentric shells, they will start coming close to each other in each of the concentric shells. And as a result, all of a sudden, explosive nuclear burning will start in all the cells almost simultaneously. Now can you imagine? What is it like that? Imagine a sack of chocolate bombs where all the bombs are ignited at the same time. I just can't think about it. Now, something even more drastic happens after that. As a result of all these almost simultaneous thermonuclear reactions going on, what will happen? More and more photons will be created, right? Now, as more and more photons will be created, they will be again converted to electrons and positrons. So, at least as a result of the thermonuclear reaction rate increasing, more photons were increased. So, maybe the radiation pressure could have regained. But instead, because of the high rate of production, again the created photons, most of them will be converted to electron-positron pairs. So what will happen? Overall, there will be more and more dominance of gravity. And as a result, the collapse will happen even faster. And the rate of the nuclear reactions will increase even more. And what will happen is that in a matter of seconds, their result, well, I was not there, neither any of us to observe this. These are results of simulations. In a matter of seconds, this heavy mass star burns out. Entire star, all the shells, they start burning simultaneously. And this causes a huge explosion. You understand? This is a different type of nature of the collapse. So when I will ask you in the examination, the difference between core collapse supernova and pair instability supernova, you must mention, because there is explosion in both cases. In core collapse supernova, what happens is that there is sort of matter is getting crushed near nucleon densities. When it comes, it is already the inside neutron star is slowly being formed, and the outside crust it comes falling apart inside. But when it starts crushing, coming near the neutron, near the core, it gets rebound. Why? Because of the hardcore nuclear interaction, right? Nucleons can't be squeezed all of a sudden. So as a result, it gets rebound. And after that there is neutrino reheating, which again accelerates the rebound. And so this is the reason for the explosion in core collapse supernova. Whereas here what is happening is when the gravity is crushing the matter inside, all of the levels, concentric shells inside. Okay, so if this is the star, these are the concentric shells. Okay, then in all of them, simultaneous nuclear burning will start. Huge energy will be released, and all energy means photons, I am saying, right? And all the photons, if they convert slowly, most of them, they convert into the electron-positron pair, the gravity will be even more angry. Well, there is no one there, let me even crush it even more. And this will cause the rate of nuclear reactions to again increase even more. Remember, the rate of nuclear reaction is very much temperature sensitive, and as a result more and more energy will be released, and this entire stuff will be exploded away without any remnant. So in the case of pair instability supernova, you will not observe any remnant, no neutron star, no black hole. Whereas in the case for core collapse supernova, you will observe either a neutron star or a black hole. Now the same thing happens for thermonuclear supernova as well. There also, what happens in the case of thermonuclear supernova, we have got a red giant star and say a white dwarf. Now, as the matter slowly gets accreted in the white dwarf, its mass increases slowly and slowly and slowly and slowly until it reaches the Chandrasekhar mass limit, where it can no longer withstand the electrons inside this white dwarf, can no longer withstand the gravitational pressure, right? The force due to gravity, and as a result it collapses. And because of this again collapse, what will happen is all the concentric shells inside the white dwarf, they will again start burning. Okay, why will they start burning? Because all the nuclei in each of the cells, they will come closer to each other. Shells will reduce, so the nuclei will come close to each other. The temperature is increasing, density is increasing, so nuclear rate will increase. So the same thing will happen over there. In the case of thermonuclear supernova, the explosion will happen. And so, both in the case of thermonuclear supernova and core collapse supernova and pair instability supernova, no remnant will be present. Okay? Any questions regarding this? Remember, the origin of the explosion for core collapse and pair instability are different. So I might ask you to distinguish between pair instability and core collapse supernova in your examinations.
Sir, pair instability is multiple explosion of the
multiple explosion, where you can say successive, gravity keeps on pushing, slowly the shells are being burnt up. Okay, now this is all theoretical predictions, but again in these two scenarios, thermonuclear supernova, this I don't know, but you can say, but the time difference between those successive events will be very small, because it is predicted that in a matter of seconds or minutes, the entire star will be burnt out. That's the fact.
So how do the radiation pressure, gravitational pressure balance?
How? You see, the origin is not the production of photons to electron-positron pairs, but the origin of this entire problem is the high rate. They can be converted. In fact, in normal star, even also there is some photons which get converted to electron positrons. That's not the issue. The issue is the high rate, and this high rate is because of these two stuff. This inhibits. This in fact favors that photons, they can just travel, they will not be absorbed and all that. And this range is basically the one which helps the increased production of the electron positron pairs. So in the case of say stars with mass less than 130 solar mass, what will happen? The production will be there, but it will not be that much large that the explosion or pair instability supernova will happen. So if the mass is less than 130, this balance will be disrupted somewhat, but supernova is not theoretically predicted if the mass is less than 130 solar masses. Okay, keep these points in mind. কি অবস্থা বুঝতে পারছো?